Hello everybody. So now we will talk about the second case in the unidirectional diffusion without chemical reaction, which is the pseudo steady state. And before we talk about the equations and the derivations, I would like to talk more or to talk first about the term. What do we mean by pseudo steady state? Pseudo steady state means that it is kind of fake steady state, so it's not an actual steady state. When we talk about or say this term, we mean that it is almost a steady state process. So we have a lot of conditions that are similar to the steady state conditions. We have constant concentration difference. We have constant boundary conditions. So everything is constant. We don't have any time dependence whatsoever, which is we can talk about, except for one important difference, which is that one of the boundaries is moving very, very slowly with time. So this is the main difference here, that one of the boundaries moves very, very slowly with time. And when we say it's very, very slowly with time, we can say that it is very similar to the steady state. Because we don't have like a very fast change of the movement of the boundary with time, and this means that the diffusion distance is almost constant for a short period of time, and it's kind of visible in large or long period of time. So this is what we can consider as the pseudo steady state. So we apply the steady state conditions to the molecular diffusion equation, and then we deal with the motion or the movement of the boundary in another way, and that's why we call it a pseudo steady state. So we apply steady state conditions with some manipulations after that. So one famous example of the pseudo steady state is the Arnold diffusion cell, but this is not the exact Arnold diffusion cell like before. So it's very similar to the previous case. So in the previous case, we had this reservoir here in the bottom, which is connected to the capillary tube, and this reservoir would compensate any losses that take place due to the evaporation. So the height here was constant. The boundary is always constant. Z1 does not change with time. After 10 minutes, after 1 hour, after 2 hours, it's always gonna be the same. But in this case, we don't have a reservoir. We have a capillary tube that is closed from the bottom. It's filled with the liquid, whatever this liquid is, and the losses in the liquid due to evaporation are not compensated, and this leads to the reduction in the height of the liquid in the capillary tube. So we start here with a small diffusion distance, and then after some time the diffusion distance is larger. And this takes some time. So this is an experiment that's it's done to predict or calculate the value or estimate the value of the diffusion coefficient in gas phase, the binary diffusion coefficient in gas phase, and this is or the calculations are done based on this assumption of pseudo steady state. And the experiment is mainly or the outputs of this experiment is the height changing with time. And this in this experiment we take reading maybe every 30 minutes or so, and in 30 minutes you would notice 1 millimeter, 2 millimeter reduction in the height of the liquid, which is not too much. So the assumptions of steady state is kind of a valid assumption in this case. So we still have the same conditions. We have an airstream here that is purging the liquid or the vapors from here. The boundary condition here is still the vapor pressure. The boundary condition here is still 0. So the only difference is that the distance is changing with time. And this is important because this is one thing that we will notice in the equations when we deal with them. So still, again, this is what we said, it's pseudo steady state. So we can say that we will do balance equation or mass balance or mole balance on the liquid interface. So we'd say that the flux of the vapors that are diffusing from the interface towards up equals the mass, or the number of moles of the liquid that are reduced in this height. So if I have 100 moles that evaporated, then the height that is decreasing here is the height corresponding to 100 moles of the same component. So this is what we are going to do for this part, which is related to, or which is written in red, which is related to the diffusion in the gas phase. We are going to get this part of the equation from the molecular diffusion equations and the continuity equation. And for this part, we will do the calculations on the liquid part, which is just change in the height. And then we'll see how we can relate the change in height with the number of moles. So for the first or the left hand side of the equation, we can use the same form that we used before, because it's exactly the same process, with one difference here. In the previous case, we had the equation written in terms of Z1 and Z2, which were constants. In this case, I cannot consider Z1 minus Z2 equal to be a constant value, so we will put, instead of Z1 and Z2, just Z, which is the height of the diffusion height. This is the main difference. I'm keeping this as a variable because I have variable height, so I cannot put a constant value. So this is one very important point here. The rest of the equation is the same, it's just the Z. And for the second part of the equation, or the right hand side of the equation, it is the NAZ is d by dt, which is the change with time of the number of moles per unit area. This is the definition of the flux. It's the change of the number of moles per unit time per unit area. And then the number of moles are the mass divided by the molecular weight, and the mass of A is the rho. And keep in mind that this is not a mass concentration, this is the density of a liquid, because I'm applying this equation to the liquid phase. So this is the density of the liquid multiplied by the height, which is A multiplied by Z. But in this case, density of a liquid is constant because I'm operating at constant temperature. A is constant. I have a constant cross-section area of the whole tube. Molecular weight is constant, so I can cancel A with A because I have area in the denominator and numerator, and get the rest as constants out of the differential. So you will end up with rho divided by molecular weight multiplied by dz by dt. And then we can put the two sides of the equation, or substitute with the two terms in this equation, which will be what we see here. Everything here is constant except for Z. I have C, D, A, B, Y, A1, Y, A2, Y, B, L, M, rho, A, L, M, A. They are all constants. And we can rearrange the equation so that we have the constants as one term, and we have the integration of dt from t1 to t2, and integration of z dz from zt node to zt. And very, very simple integration. We can do the integration, and this is the equation that we are getting. I can take all these terms as one single term and call it S, to just group them and give them a symbol which is S. And then the equation can be rewritten in this simpler form. I want to remind you that this experiment is done to get the value of the diffusivity. So if I can get the value of S, and with the knowledge of all the rest of the terms here, I can get the diffusivity. And this is the equation based on the knowledge of the term S and the rest of the terms. To get the term S or get a value of this, you can think of this, that I just need two heights and the difference in time between these two heights. So the experiment, when we do the experiment, this is the output that we get from the experiment, that we have a table with times. So I do the experiment or take a reading every, let's say, 30 minutes. So I take a reading at time equals 0, 30 minutes, 1 hour, 1.5 hour, 2 hours, and so on. And for each time I get the corresponding height. And for each height or for each data point, I calculate z minus zt square, zt minus zt naught square divided by 2, and get these values. And from the output, I can put the values and draw a straight line that is the best fit, which passes by most of the points or close to them. And from the slope of this equation, or from this plot, the y-axis is t, z-axis, x-axis is z t square minus, which is this bracket here. And from this, I can get the slope of the plot, and from the slope, I can get the value of s. And this is how we get the diffusion coefficient. But before we pass this point, I want to discuss one important point, which is one valid question that you might ask, which is why do I have to get all these data points, and why do I have to draw a plot, get a slope, so that I can get the value of s, while I can just pick any 2 points and substitute here in this equation. So I can take t node and t1, I get the difference between these 2 points, and z square and d square, I have these 2 values already, and it's going to be just direct substitution in the equation, and you get the value of s very, very simply. So this is a valid question, and the point here, which is an important point, is that if we assume that you can do this, then let's say somebody would pick these 2 points to calculate the diffusion coefficient. So the value of s that he gets is t divided by this bracket, which is the slope, which is the slope of this graph. So if you pick these 2 points, then you have a slope which equals to this, which passes of the slope of a straight line that passes by these 2 points specifically. And maybe somebody else would think of picking 2 other points, so he would pick these 2 points, and then he's gonna get a very, very different slope. So you can see this is the actual slope that you get, and you have this slope, and somebody else has this slope. So the values of d that you are getting from the 3 graphs are very, very different, and they're not accurate at all. And the reason we have this problem or these discrepancies is that when you do the experiment, there is always a chance of having an experimental error. This might be an error because of the time that you took the reading in is not very accurate. When you took the reading, there is a human error. When you calculated the exact height, it might not be very accurate. There might be an error due to the conditions. Anything that that can happen during getting the data points, or during setting up the experiment, or getting the results, or anything. So it's a very, very big chance of getting values that are not very accurate. They're close, but they're not very, very accurate due to the experimental error. It's a human nature. You must do some human error. We're not machines, and this is why we need to get many points, at least 5-6 points, so that you can put them together. You see how they look like, and you get the best fit that passes by most of them, so that you can reduce the experimental error. In some experiments, they would take 20 or 30 data points to make sure that they have enough points to get reliable results. So this is the reason why we go through this long procedure. In the next video, inshallah, we will solve another example on the pseudo steady state and see how we can apply it on a different system, which is a solid phase system. So I'll see you then, inshallah. Goodbye.